Okay, our next talk is a Heterogeneous Execution Engine for LLVM by Christos Margiolas from University of Edinburgh.
Hello all. Thank you for being here. So this presentation is about a Heterogeneous Execution Engine for LLVM. So what I mean by saying this? So Hexe is a set of new compiler passes and runtime environment targeting the transparent execution of existing and straightforward software on heterogeneous platform. So we have a set of new compiler passes, a runtime environment. We have a modular design, meaning that we have the core part of the project being independent of a specific platform and architecture, and then we have plugins for specializing. And the idea is that by having this design, we extend natively the LLVM infrastructure. Okay, so let's first define what is a heterogeneous system. So a heterogeneous system typically is a platform where we have more than one processor type. So in this high-level abstraction, we have two components, the host platform, where the CPU cores live with the main system memory, and the device component, where we have a set of accelerator cores like GPUs, DSPs, Xeon Phi, etc., and maybe a dedicated memory subsystem. And the typical action that happens between the host component and the device one is that we have communication, which takes place in both directions. Of course, as I said, this is a high-level abstraction. We may have different configurations where we may have a single die with CPU and GPU cores sharing the same memory subsystem, etc. Now I would like to define what is the key concept for heterogeneous computing. And this, I think, is the workload offloading concept, meaning that every time we want to offload something, to dispatch something for execution on the accelerator, there are a number of steps that we have to follow. First of all, we have to share the data between the host memory and the accelerator one. This may involve an actual data copy, or we may have hardware coherence, where we just have to make sure that we flush the caches, etc., and whatever it's necessary. Then the next step is that we have to dispatch the kernel for execution, where we provide the arguments, the kernel, and we dispatch to the device. And the device with accelerator cores performs the computation. Then, when this step is done, we have to copy the data back. So, and this, again, it may require an actual copy, or we may just rely on the hardware coherency. And this kind of concept, I believe, is shared across all the available frameworks for heterogeneous computing and graphics computing, talking like OpenCL, CUDA, DSP SDKs, OpenGL, and even CellB in the past. So what are the existing solutions for heterogeneous computing right now? Of course, we have programming models like OpenCL and CUDA, where the developer has to use a completely new, different programming model and write code explicitly for the accelerator. Then we have language extensions like OpenMP or OpenAC, where we either use some pragmas or some actual new language expression to express a piece of code that we want to run on the accelerator. Then a new and modern trend is to define domain-specific languages, where it's quite easy to write code for targeting special accelerator architectures. And for doing all this, usually we have source-to-source compilers that do a set of text transformations to make this happen. So what are the upcoming issues with this approach, at least based in my opinion, is that we ask from the people to use a completely different programming model. We require them to do a significant development effort. There is no actual compiler integration. There is front-end compiler integration, but not intermediate level integration, which I think is quite important for optimizing. And then there is no integration with existing JIT technologies. We cannot, for example, combine MCJIT with OpenCL or CUDA. We need something that is in a lower level so we can combine those two pieces together. And finally, the current approach is kind of very specific. We target a language like CUDA or OpenCL. We target a platform, let's say GPUs. And then we target a processor, which may be a vendor-specific GPU like NVIDIA, AMD, or Intel, or others, sorry. So here I'm trying to visualize what I would like to communicate here today. So we have this dump implementation of memory copy, where, as you know, we have the destination and the source, and we copy a number of bytes. So if we write this code, it's super simple to run it on the CPU. We just compile it. We have a very well-defined programming model and conventions that we use for decades, so we just compile it and run it. Now, what happens if we want to run the same piece of code on an accelerator? So there are options here. As I said, we can use OpenCL, CUDA, or another framework. But this requires significant effort. The developer has to write by hand the code, change the form, use a different programming model. And the situation gets a bit trickier because there is not a very standard programming model in the environment. Every vendor and every type of accelerator needs different type of execution environment and many times a different programming language. So we may work this out, but requires a lot of effort, and it's not really, really portable. So the real question is that what happens if we have a system where we care to dynamically dispatch a piece of code, either on the CPU or the accelerator, or a mix of them? That usually requires the developer to write a different code for every processor type. But what we see is that this is not portable, it's not definitely transparent, and we have to know the target platform ahead of time, which is kind of difficult, especially for realistic deployments. So Hexe, the heterogeneous engine I'm presenting today, targets to solve this problem. So as I said, we use a new set of compiler passes and runtime environment where manages transparently code offloading on either CPU cores or accelerator resources, accelerator cores, etc. And this is done in a portable way. We support dynamic scheduling, and we try to be as neutral as possible to vendor-specific solutions. Here I present an overview of the compilation procedure, which is now broken down in two steps. The first one, we care to compile the source code for our host architecture, creating the host binary, the piece of code that will run on the CPU cores. In this example here, I assume that the code is C or C++ sources, and we use Clang to generate LLVM IR. This may not be the case. We may have a virtual machine generating LLVM IR, or having another front end, for example, for a functional language. So what happens is that we perform the typical optimization pipeline, then we intervene with my new compiler passes, the workload analysis and workload extractor, where the second extract a new compiler module that contains the code that we want to run on the accelerator. Then we optimize again. We compile for the target CPU architecture. We link against the Hexe runtime library, and we create a binary. Now what we do with the new module, the Hexe workload IR we just generated, we have a second compilation step that aims to compile this module for the accelerator architecture. So again, we have a new pass here called workload transform, which pass is responsible for transforming the IR to be compatible with the target accelerator architecture. So how the actual binary works out and how we have something running. So what happens is that we have the typical process creation procedure where the operating system loads the host binary in memory, then the standard environment gets initialized, then we initialize the Hexe runtime, the Hexe environment, which loads the accelerator binary to the memory and makes sure that the programming environment of the accelerator is initialized properly. And then the application executes, and then we terminate. So this model, I think, is quite close with what CellB was using in the past. And of course, the binary we use are target-specific. But we hide all these details with plugin interfaces. So now I'm going to talk a bit more in detail about the compiler passes. I'm going to talk first about the compiler analysis and then the workload extractor. So the aim of workload analysis is to analyze loops and functions and decide if we can offload them based on a small number of very basic criteria. And then the extractor uses this information to extract piece of code and transforms the host code and injects calls to the runtime library. So we can call transparently our runtime and offload something to the accelerator resources. So workload analysis. It's a modular analysis pass. It's target independent, and it investigates the eligibility of workloads. The types of workloads we currently consider is a call to a function or a loop. The key assumptions are that we have quite different host and accelerator architectures. We may have different types of memory available on a platform, like we may have a fully coherent system and one-way coherent system, or having a system without any coherency. And the origin of the source code may be C, C++, other high-level languages, or even a virtual machine. Think a case, for example, having a browser with the LLVM JIT generating code that you could run on the GPU. So the analysis, we have two analysis steps. The first one is that we investigate code eligibility and then memory reference eligibility. So what's this? For the code eligibility, we inspect the type of instructions. Because we have two architectures that they are quite different, we don't have any guarantee that they support the same type of atomics, they support the same type of special instructions, and they support exception handling. So we constrain our analysis of not supporting for offloading code that contains atomics, LLVM intrinsics, with the exception of the basic memory operation intrinsics. We don't offload code that contains other function calls, and we do not support exceptions. Of course, some of these can be relaxed, but at this point, it's better to have something working which makes sense for computational intensive processors than trying to cover an exception case or something really advanced and tricky. Then we have to analyze the memory references of the piece of code we consider for offloading. The reason we do this is that we want to clone a piece of code in a new module that is going to run in a completely different architecture. And we don't have any guarantee about the level of memory coherency and if a pointer or something is valid to the accelerator side. So we require that the function that we offload only access memory via its function interface or global variables. The case now for loops is that we only support memory accesses that come from the host function interface, the function that contains the loop, or global variables. And we keep track of this information because we need it later for the actual workload extraction. Okay, here I have a very simple example where I show when it's valid to offload something and when not. So in the first example, we do a trivial computation where we read an array, a special index inside the array, we add the value and we return it. So this piece of code only accesses memory via its function interface, so it's okay to offload. The second example is a variation of this, where we access both a memory reference by the function interface and as a global variable, which is still okay to offload. In the third case, we do a typical CV type casting where we just use a raw address and we perform a computation. This thing cannot be offloaded. Sorry, if? Yeah, but the problem is that these address that you have, it may be valid on the host architecture, but maybe not on the GPU context, because you don't have any guarantee about how the programming environment of the accelerator behaves. Yeah, I mean, yeah, in a real example, you just eliminate this, right? Then I'm going to talk about the workload extractor, which is the transformation pass that converts the host code in order to support transparent workload offloading. So I provide a set of utility functions, classes, sorry. The first one is responsible for extracting code and cloning it in a separate module. The second one changes the control flow of the host code and inject runtime calls. And these calls take care of the offloading, like deciding about scheduling, offloading, data sharing, etc. So the whole design is very modular, so it's very easy for people to dig in and specialize the way they want, and, for example, have their own cost models to decide if they want to offload something or not. So here, let's talk a bit about how we extract code for the Hexe workload module. So what we do is pretty much we clone function and loops to the new module. For functions, we just clone them. For the loops, we have first to extract the loop, make it a function, and offload it after. And of course, we preserve the original code on the host module. And the reason is that we may have a runtime decision saying that the GPU is down, the accelerator is down, or it's busy, so we want to run something on the CPU. Or we may have runtime decisioning about the type of workload and where we would like to run something. So at this point, we have the original LLVM module, and we have the newly created Hexe workload module. Next, let's see how we transform the original code to support the transparent offloading. So consider the original basic block where we have a set of n instructions, and one of them is a call instruction that calls function f. And this is the workload we care to offload in this particular example. So what we do here is that we create a divergent control flow where we have two paths. the host basic block, where we perform the execution of the workload on the CPU, and the offloading basic block, where we perform a number of steps in order to run the same code on the accelerator, the device side. This decision, if we are going to run on the CPU or the accelerator, is done based on a runtime call to our runtime library that decides on the fly what we want to do. Now, for offloading a workload, we need to enforce coherency, do data marshalling, dispatch the workload, wait for completion, enforce coherency again, and read the return value if there is one for a particular function. This is done in a generic interface, which is completely independent of if we use OpenCL, a specific DSP SDK or something. So we build a unified interface. And then on the runtime side, we handle the specialization. Next step. As I said, the compilation is now split in two sides. The first one is compiling for the host architecture, and the second one is compiling for the accelerator side. So here we have a new compiler pass called the workload transform. And the idea here is that we take IR, that it was meant, for example, for x86 or ARM architecture. And now we have a GPU architecture, a DSP architecture. So a lot of things may be different. We may have a different number of work size. We may have 32-bit versus 64-bit. We may have different stack alignment, NDNS, ABI, etc. And we may also be enforced to follow specific function interfaces or use runtime calls based on the programming environment of the accelerator. So for example, if you use OpenCL, you have to use the built-in functions of OpenCL to find your way how to compute the data, how to access memory, how to read an image, etc., etc. So what happens here is that we take the extracted workload, the Hexe workload, we feed it to our transformation, we optimize it, and then we build a binary for the accelerator architecture. So until this point, all the techniques I described, they are completely generic. They have nothing to do with a specific host or accelerator architecture. So how do we specialize about this step? Because we compile for a particular accelerator binary, so we have to be aware of the exact architecture. So we provide an adapter interface where we have the core functionality being independent of the vendor, and then we use that interface to specialize the workload transformation for a particular architecture. So far, I'm supporting a debug adapter where I offload things on workloads on the same architecture where the host works. I have an OpenCL adapter where I support execution on OpenCL capable devices like GPUs. And then I have a completely different type of accelerator. I support the Hexagon DSP, which is a completely different universe than what you expect from the GPU ecosystem, but it works pretty well, and that I think is a good point why the whole approach is quite generic and can cover different range of systems. So that's the plugins I have so far. Next, I would like to talk about the runtime environment. As I said, the runtime environment plays a key role here because it's the component that controls the actual offloading. Handling things like data sharing, memory coherency, the actual dispatch. I provide an event interface for asynchronous offloading, and I provide special memory allocation functions, which are optional, but in some platforms they may deliver higher performance. And I will explain a bit later. So the idea about following this design is to have a very minimalistic and simple runtime environment, which can be run in an embedded system, but also in a desktop system, a data center. So I want to be quite lightweight. I use a plugin interface that relies on virtual tables. The runtime is written in C, so I'm using the approach of the Linux kernel for doing virtual tables. And the asynchronous offloading, it's a concept that works well in runtime, but currently is not supported from the compiler perspective because it's quite tricky to auto-generate code that does automatic offloading and make sure that you can have some actual gain, performance gain. Next, an important task that I should probably spend a lot of time talking about is data sharing management that is done by the runtime library. So as I already described, we may have completely different architectures. We may have a heterogeneous system with no memory sharing or coherency, where explicit communication is required We may have full hardware and driver support for data sharing, where we have virtual shared memory, as it happens with CUDA and OpenCL version 2. And we may also have special memory pools that guarantee improved performance, or just data sharing between the different architectures. So we need to follow a design which is generic enough to cover all the cases. So the idea is that we have plugins for every potential platform and specialize in there. For example, in the current status of the project, I have again an OpenCL plugin, I have a Hexagon DSP plugin, and I have the debug plugin again. So based on the platform capabilities, we may have to take a set of special actions, like track the memory allocations of the host program. And this happens because, for example, imagine that you have a program where the user uses standard malloc and new, and the accelerator is a GPU with the capabilities of OpenCL 1. In that case, you don't have any kind of sharing, so you have to perform an explicit data transfer. So we need to be able to track the memory allocations on the host and transparently perform the communication operation as part of the plugin of the runtime environment. As I said, yeah, we may have to handle explicit data transfers. We may have to utilize special memory pools, something that is very popular in the embedded area with DSPs and GPUs. And of course, if there is hardware and driver support that can give us efficient data sharing with zero copying and all the fancy new features, of course we use it. And that's the case of HSA with OpenCL, the CUDA unified addressing, and the OpenCL version 2 with the shared memory model. Sorry. Now let me talk how this heterogeneous engine integrates with the rest of the LLVM ecosystem. So I have done some work in combining Hexe with MCJIT. So the idea is that we have an LLVM module coming from a source language like C or C++, or may have a virtual machine generating LLVMR on the fly. So before we feed the module to MCJIT in order to create on the fly code to run on the system, we intervene with a workload analysis and a workload extractor passes. So we decide which workloads we may want to run on a GPU. Then the updated version of the module with the support for offloading gets fed to the MCJIT, and MCJIT does the typical JITting compilation, with the difference that now we may have the option to offload something to our GPU. So for example, you can think like having your web browser and having something that is computationally intensive on the fly and decide to run it on the accelerator. The next thing, which I think is a bit tricky, is that by having this new two-step compilation model for the accelerator, we may want to vectorize or auto-parallelize code. And actually, that's what I do for the OpenCL adapter of Hexe. I have to auto-parallelize first and then generate LLVM IR that is OpenCL compatible. So I believe that picking the right vectorizer and parallelizer can be quite tricky, especially if we consider the diverse hardware systems, hardware architectures. And I think that existing projects like Poly or other open source parallelizer can play an important role, either for vectorizing or auto-parallelizing. Next, I would like to show some results. It's something very basic. I don't think I have time for a full evaluation of the current status of the project. So what I have here is that I'm trying to compare the performance of Hexe against a human-ported version of a benchmark to a specific accelerator processor. So in this example, I consider the Snapdragon DSP and an NVIDIA K20 GPU. So the baseline here is that a developer's port to the accelerator environment. So as you can see, there is some variation, but there are a few cases that we do better, like ATAX, than the human-written version, and there are others, like MVT, that we do far worse. And the reason for this is that we handle data transfers in a completely different way, and second, the code we auto-generate for the accelerator is not always the optimal case. For example, when you decide to write OpenCL by hand, targeting a GPU, you spend a lot of time reading the GPU architecture and specialize about finding the ideal number of threads, the ideal number of scratchpad usage, etc. But overall, I think as the first generation of results, I think they're quite good, and of course they can be improved in the future. So conclusion. So this presentation is about Hexe, a heterogeneous execution engine for LLVM, which introduces new compiler passes, a runtime environment, has a modular design, which covers a diverse set of heterogeneous systems and extends the LLVM infrastructure. So that's what I would like to talk about. So I would like to get some feedback right now, try to talk a bit about the technical details, and if someone is interested to learn more about how the adapters or the plugins have been designed, for example, for OpenCL or Hexagon, I'm happy to talk about. But I thought it's a lot of detail at this point to talk about a particular plugin. Thank you.
Thank you to our speaker. Do we have any questions? We have about 20 minutes till lunch, 15, 20 minutes.
So your global variables that you mentioned that you showed in the workload, are those handled by the runtime environment,
Yep.
or how do they get shared? Because you don't know the addresses during the IR generation, so it's done through the...
It's handled by the runtime. So the runtime, if you don't have any level of coherency, you have to track the dynamic memory allocation, and you have to use the ELF library to analyze your data segment so you know the size and the symbols and how much memory they allocate.
Okay.
So you keep track of this information. So dynamically, when you decide to offload something, you find if it's a dynamic allocation, if it's a global variable, and do the necessary data transfers.
Is it pretty efficient? Is it smart enough to only know which memory is actually going to be shared and then have to copy that? So it's not going to go over like everything in global space?
No, I mean, what happens is that when the Hexe runtime initialize, reads all the data segments, so you can find all your global variables and their allocation. But for all the dynamic memory allocation, the writing happens during runtime. Okay. So you just intercept the standard memory allocation functions, and you keep track of every allocation and its size.
One other question, sorry. How does this overlap with the HSA, the heterogeneous system architecture support? Like, I assume here you're looking at extracting workloads, right, from within the same kind of program flow, but I know there's this separate approach for things like system on a chip where you have different architectures that are running pretty much different workloads, and you don't necessarily want to overlap them. Have you interacted with that effort at all? Because it seems like there's an overlap in trying to produce these different different binaries for different target architectures.
Okay. So if I understand what the correction is, that what's the relevance of Hexe with the existing heterogeneous computing approaches like HSA? So I think they're quite compatible, because Hexe, what provides you is a transparent automatic way to extract workloads and then run them on the accelerator resources. Then, by having a proper plugin interface, you can exploit HSA through OpenCL or via the low-level HSA runtime library and take advantage of the underlying architecture. So the idea is to provide a portable generic interface and then specialize both on the compilation stage for the accelerator and the runtime side via the plugin interface.
Thank you.
Any other questions? No? All right. Thank you very much.
Thank you.